Hello, all. Hope you're doing well today. Today we're finishing up chapter 4, Biomechanics. This is part 3. Here we go. Mechanical advantage refers to the ratio of the output force or the force applied by a machine or system to the input force, which is the force applied to the machine or system. It quantifies the amplification of force or advantage gained by using a machine or mechanical system. It is a measure of how much a machine multiplies the force or changes its direction to make it easier to perform a particular task. You can see that in the picture here on the right, of course, using a lever to help in moving the load. There are two common ways to calculate mechanical advantage. First is output force divided by input force. This formula calculates the mechanical advantage based on the ratio of the output force to the input force. It gives a numerical value in representing how many times the force is multiplied or changed by the machine. Mechanical advantage, looking at distance of output force divided by distance of input force. This formula calculates the mechanical advantage based on the ratio of the distances traveled by the output force and the input force. It indicates how much the machine multiplies or changes the distance over which the force is applied. Mechanical advantage can be greater than or less than 1, or it can be equal to 1. Here's what each scenario represents. MA, your mechanical advantage is greater than 1. This indicates a mechanical advantage greater than 1, meaning that the machine amplifies the input force. It allows a smaller input force to exert a larger output force. Examples include levers, pulley systems, and hydraulic jacks. Mechanical advantage is equal to 1. Indicates that the machine does not multiply the force or change its direction. Input force and output force are equal. Examples include simple ropes or cables used for lifting objects without mechanical advantage. And mechanical advantage is less than 1. This represents a mechanical advantage less than 1, indicating that the machine requires a larger input force to exert a smaller output force. In this case, the machine trades force for a favorable change in direction or distance. Examples include inclined planes and some types of gears. Understanding mechanical advantage is essential for evaluating and designing machines and mechanical systems. By manipulating mechanical advantage, engineers, designers, and exercise scientists can optimize the performance and efficiency of various mechanisms, making tasks easier, safer, or more efficient. Mechanical work is a concept in physics that measures the transfer of energy when a force acts on an object and causes it to move in the direction of the force. It quantifies the amount of energy transferred or expended during the process of performing physical work. The formula for calculating mechanical work is equal to force times distance, where work is the amount of energy transferred or expended measured in joules or often in watts. Force is the magnitude of the force applied to the object measured in newtons. And distance is the displacement of the object in the direction of the force measured in meters. Mechanical power refers to the rate at which work is done or energy is transferred in a mechanical system. It measures how quickly or efficiently work is performed or energy is transformed. Power is a crucial concept in understanding the performance and efficiency of machines and mechanical systems. The formula for calculating mechanical power is equal to work divided by time, where power is the rate at which work is done or energy is transferred measured in watts. Work is the amount of energy transferred or expended measured in joules, and time is the duration over which the work is done measured in seconds. Alternatively, power can be calculated as the product of force and velocity, where force is the magnitude of the force applied to the object measured in newtons, or velocity is the speed or rate of displacement of the object measured in meters per second. Power is the amount of energy transferred or converted per unit of time. It's measured in watts. Power in the performance of certain activities requires the ability to generate high forces while moving at a high rate of speed or high velocity, such as jumping, throwing, power cleans, kicking, and martial arts. Strengthening a muscle increases the force applied and results in greater power output. Mechanical energy refers to the energy possessed by an object or system due to its motion or position. It is the sum of kinetic energy and potential energy associated with the object's mechanical properties. It can be linear or angular. Kinetic energy is energy of an object in motion. It is directly related to the object's mass and velocity. The kinetic energy increases with both the mass and the square of the velocity of the object. This means that faster moving objects or objects with greater mass have higher kinetic energy. Potential energy is the energy possessed by an object based on its position or condition. There are different types of potential energy, including gravitational potential energy, which is a function of body's height above a reference level, elastic potential energy, and chemical potential energy. There's also energy of position or deformation that causes a strain, and this is energy that's stored within a body when it's deformed, such as a tendon or ligament or a pole vaulter's vault. Now, the conservation of mechanical energy, according to the law of conservation of energy, mechanical energy is conserved in a closed system where no external forces such as friction or air resistance act on the object. This means that the total mechanical energy, which is the sum of kinetic and potential energy, remains constant, and it only transforms from one form to another. Mechanical energy can be converted from one form to another. For example, when a ball is thrown upwards, it initially has high kinetic energy, but as it reaches its highest point, the kinetic energy decreases and it's converted into gravitational potential energy. As the ball falls back down, the potential energy is converted back into kinetic energy. Mechanical efficiency and movement efficiency are related concepts that refer to how effectively energy is converted into useful work or motion in a mechanical system or human movement. Mechanical efficiency measures the effectiveness of a machine or mechanical system in converting input energy into useful output work. It is the ratio of the useful output work to the input energy work. Movement efficiency refers to how effectively the body or an organism performs a particular movement or physical activity while minimizing energy expenditure. It involves using the least amount of energy to achieve a given movement or task. In human movement, factors such as technique, biomechanics, coordination, muscle activation, and economy of movement play important roles in movement efficiency. Efficient movement patterns optimize muscle recruitment and reduce unnecessary movements and minimize energy wastage. Movement efficiency can be enhanced through practice, proper technique, strength training, flexibility, and neuromuscular coordination. Improving movement efficiency can lead to better performance, reduced fatigue, and improved endurance in activities such as sports, exercise, and daily tasks. Mechanical efficiency of machines is relevant in the context of energy conversion and work output. In contrast, movement efficiency focuses on optimizing movement patterns and energy expenditure in human locomotion or physical activities. While mechanical efficiency relates to the performance of machines, movement efficiency pertains to human movement, biomechanics, and energy utilization. Enhancing movement efficiency can contribute to improved mechanical efficiency when human movement is involved in operating machines or performing work. Optimizing both mechanical and movement efficiency is important for enhancing performance and reducing energy waste and improving overall efficiency in various contexts, whether it be in machines, sports, exercise, or daily activities. Muscle is one of the four primary tissue types of the body. Muscle cells are specialized for contraction. Muscles allow for motion such as walking. They also facilitate bodily processes such as respiration and digest. All muscles share several properties: contractility, excitability, extensibility, and elasticity. Contractility is the ability of muscle cells to forcefully shorten. Contractility allows muscle tissue to pull on its attachment points and shorten with force. Muscles can only pull, they never push. Excitability is the ability to respond to a stimulus, which may be delivered from a motor neuron or a hormone. Extensibility, on the other hand, is the ability of a muscle to be stretched or extended, and elasticity is the ability of that muscle to return to its original length when it's relaxed. Here we're looking at muscle fiber arrangements and an example of each of these that you can see. Each fascicle or fasciculus is a bundle of muscle fibers, also called myocytes. They're bound together via the endomysium tissue that provides pathways for the passage of blood vessels and nerves. There are 4 distinct patterns of fascicles that are seen within the whole of the muscle. They're parallel, convergent, pennant, and circular. Parallel fascicles lie parallel to one another along the longitudinal axis of the muscle. Parallel muscles may narrow to a tendon at each end, forming a fusiform muscle, which you can see here in the lower left-hand corner, which is an indication of the bicep brachii. Or they may form wide, flat muscles with wide, flat tendons, or aponeurosis, typical of abdominal wall muscles like the rectus abdominis in L. A convergent pattern is found in triangular shaped muscles, in which fascicles attach along a broad tendon at one of the end of the muscle and converge to a narrow tendon at the other. Fascicles in a pennate pattern are attached like plumes of a feather to an elongate tendon. This is typical of muscles of the limbs. The fascicles may be attached only on one side of the tendon, meaning it's unipennate. You'll see there on the lower right-hand corner, and that's looking at the tibialis posterior, or both sides, bipennate, which is B, right up above that. A circular pattern of fascicles is characteristic of sphincter muscles that surround openings, such as the mouth or the anus. The length-tension relationship of muscle basically describes the amount of tension that is produced by a muscle as a feature of its length. That is to say, when tested under isometric conditions, the maximal force produced or measured will be different as the muscle lengthens or shortens. So why are we stronger at different joint positions? What makes us relatively stronger or weaker at different joint positions? Well, it's all to do with the overlap of the contractile proteins. Remember actin and myosin? As we flex or extend a joint through its range, the overlap of the actin and myosin contractile proteins change. And importantly, this affects the potential for the development of cross bridges and muscle force production. A cross bridge describes the temporary attachment of the globular head of the myosin filament to the adjacent actin filament. Repeated attachments and detachments that draw the proteins closer together and shorten the sarcomere describes the sliding filament theory of muscle contraction. Whilst we can describe this phenomenon during fairly gross motor skills like the bicep curl above, the initial research was conducted at a sarcomere level. Remember, a sarcomere as a functional unit within a muscle fiber. Have a look at the figure below. You'll see how the length of the sarcomere influences its capability for force production. Here you see in the picture, this is a demonstration of force-velocity relationship of a skeletal muscle of the knee extensor muscle group in a national level Olympic weightlifting athlete measured during isokinetic contraction at increasing knee flexion and extension velocities. Now, force-velocity relationship in biomechanics refers to the inverse relationship between the force exerted by a muscle and the velocity at which it contracts or lengthens. The force-velocity relationship is a fundamental concept in understanding muscle performance and the mechanical properties of muscle contractions. Here are some key points about the force-velocity relationship. In concentric muscle contractions, the muscle shortens as it generates force. The force-velocity relationship states that as the velocity of shortening increases, the maximum force that the muscle can produce actually decreases. In simpler terms, as the speed of muscle contraction increases, the force it can exert decreases. In eccentric or elongation muscle contractions, the muscle is lengthening while producing force. The force-velocity relationship for eccentric contractions indicates that as the velocity of lengthening increases, the force that the muscle can resist or produce increases. In other words, as the speed of muscle lengthening increases, the force it can withstand or generate increases. So it's exactly opposite of the concentric. The force-velocity relationship is typically represented graphically as a curve, as you see here on the right. At zero velocity in an isometric contraction, the muscle can produce its maximum force. As the velocity increases either the concentric or eccentric direction, the force is going to decrease or increase respectively. The relationship follows a hyperbolic curve, where force and velocity are inversely related. Different muscle fiber types have varying force velocity characteristics. Fast twitch muscle fibers can generate higher forces at higher velocities, making them suited for explosive movements, versus slow twitch muscle fibers that generate lower forces but can sustain contractions for longer period of time. The force-velocity relationship has practical implications for athletic training, rehabilitation, and performance enhancement. Training methods can be designed to target specific force velocity characteristics based on the desired outcomes. For example, explosive power training may focus on high velocity movements with lower forces, while strength training may emphasize slower movements with higher forces. Understanding the force-velocity relationship helps in optimizing your training programs and designing exercise regimens. Understanding the capabilities and limitations of muscles provides insights into the mechanical properties of muscle contractions and aids in enhancing athletic performance and rehabilitation strategies. Intramuscular neural adaptations refer to the specific changes that occur within a muscle in response to neural signaling and recruitment during force production. These adaptations play a crucial role in optimizing muscle force output and enhancing performance. Here's some key points regarding intramuscular neural adaptations and recruitment. Motor unit recruitment refers to the activation of motor neurons and their corresponding muscle fibers. With resistance training and repeated forceful contractions, the nervous system becomes more efficient in recruiting motor units within a muscle. This increased recruitment allows for greater force production and improved control. Synchronization of motor units within a muscle is an important aspect of muscle force production. Through training, the nervous system learns to coordinate the firing of motor units to generate a more synchronized and forceful contraction. This synchronization optimizes the overall force output and improves the efficiency of muscle activation. The size principle states that motor units are recruited in a specific order based on their size and force generating capacity. Your smaller motor units, composed of your slow twitch muscle fibers, are recruited first, followed by the larger motor units, composed of fast twitch muscle fibers. As force requirements increase, with resistance training, the size principle can be optimized, allowing for more efficient recruitment of the appropriate motor units to generate the desired force. Within a muscle, different types of muscle fibers are activated based on the force demands of the task. So slow twitch type 1 muscle fibers are recruited for low force endurance-based activities, while fast twitch type 2 muscle fibers are recruited for high force explosive activities. Through training, the nervous system becomes better at selectively activating the appropriate muscle fibers to meet the force requirements of a specific task. Resistance training and forceful contractions lead to adaptations in the neuromuscular system, including increased motor unit activation, improved motor unit synchronization, and enhanced neural drive, and improved neural coordination. These adaptations optimize the intramuscular neural processes involved in force production, resulting in increased muscle force output. It's important to note that the specific intramuscular neural adaptations can vary depending on factors such as training status, exercise type, and individual differences. However, these adaptations contribute to improved muscle force production and enhanced movement efficiency, as well as greater performance capabilities. Intermuscular neural adaptations and recruitment refer to the coordination and interaction between different muscles or muscle groups during force production. These adaptations involve the neural processes that occur between muscles rather than within individual muscles. You have a synergistic muscle activation, refers to the coordinated activation of multiple muscles and muscle groups to generate force and perform a specific movement. During force production, different muscles work together to produce and control movement. Through training and practice, the nervous system learns to recruit and coordinate the activation of synergistic muscles, optimizing their force output and enhancing movement efficiency. The nervous system establishes a specific muscle activation pattern based on the movement requirements and force demands of a task. These activation patterns dictate the sequence and timing of muscle activation during movement. With training, the nervous system becomes more efficient in recruiting and coordinating the activation of muscles in a way that maximizes force production and movement efficiency. And neuromuscular coordination involves the integration of sensory information and motor commands to produce smooth and efficient movement. It includes the timing, sequencing, and coordination of muscle contractions across different muscles and joints. Through training and practice, neuromuscular coordination improves, allowing for more effective intermuscular recruitment and optimized force output. Synchronization of muscle contractions across different muscle groups is important for efficient force production and movement coordination. The nervous system learns to synchronize the activation of synergistic muscles, allowing for smooth and coordinated movement patterns. This synchronization minimizes energy wastage and maximizes force transfer between the movements. Motor learning is a process by which the nervous system adapts and refines movement patterns through practice and repetition. It involves acquiring and fine-tuning coordination and timing of muscle activation across multiple muscles. With motor learning, the nervous system becomes more skilled at intermuscular coordination, resulting in improved force production and movement efficiency. Optimizing intermuscular neural adaptations and recruitment is important for, again, enhancing performance in various activities, including your sports, exercise, and daily movements. Through training, practice, and motor learning, the nervous system becomes more efficient at coordinating and activating muscles in a synergistic manner, leading to improved force production and movement capability. The rate of force development, or RFD, refers to the speed or rate at which an individual can generate force during a muscle contraction. It measures how quickly force is produced in a given time frame, typically during the initial phase of a muscle contraction or movement. RFD is an important factor in various athletic and physical performance activities that require rapid force production, such as sprinting, jumping, and explosive movements. Here are some key points about rate of force development. RFD is the slope of the force time curve during the early phase of a muscle contraction. It quantifies the rate at which force increases over time. RFD is crucial for activities that require rapid force development, such as explosive movements, rapid accelerations, and quick changes of direction. It is particularly relevant in sport and activities that involve high-intensity bursts of power. RFD is strongly influenced by neural factors. Motor unit recruitment, motor unit firing rates, and motor unit synchronization play key roles in RFD. The nervous system's ability to rapidly activate and coordinate motor units contributes to the speed at which force is produced. Muscle fiber composition can impact RFD. The fast-twitch muscle fibers, specifically type 2 fibers, have a higher potential for rapid force development compared to your slow-twitch type 1 fibers. Individuals with a higher proportion of fast-twitch muscle fibers can generally exhibit greater RFD capabilities. RFD can be improved through specific training interventions. Resistance training programs that emphasize explosive movement, such as plyometrics and ballistic exercises, can enhance RFD. Additionally, training methods that focus on improving neural adaptations, such as high-intensity training and power training, can also enhance RFD. RFD is typically assessed through force time curve analyses using force plates, isokinetic dynamometers, or other specialized equipment. It is expressed as the rate of force development per unit of time, and that would either be in newtons per second or newtons per millisecond. Improving RFD can enhance performance in activities that require rapid force production. Training strategies that target neural adaptations, explosive power, and rapid force development can be effective in optimizing RFD capabilities. In biomechanics, the moment arm, also known as the lever arm or the perpendicular distance, refers to the shortest distance between an axis of rotation or fulcrum and the line of action of a force. And as a fundamental concept used to calculate and understand the mechanical advantage and torque produced by a force acting on a lever. In biomechanics, a kinetic chain refers to the interconnected system of body segments and joints that work together to produce movement. It describes the transfer of forces and energy through the body during human movement. Understanding kinetic chains is essential for analyzing movement patterns and identifying potential areas of dysfunction or injury risk, and developing effective training or rehabilitation strategies. A kinetic chain involves a series of joints and segments that are linked together, and the movement at one joint or segment affects the movement at other joints or segments within the chain, such as the knees are connected to the hips, and even there are a lot of injuries that occur that really are connected to our feet, the ankles, and whether we have the mobility and stability that we need there. Kinetic chains can be classified as open or closed based on the relationship between the distal end of the chain, whether hands or feet, and the environment. So in an open kinetic chain, the distal end of the chain is not fixed and is free to move in space. An example includes performing bicep curl or leg extension where the hands or feet are not in contact with a surface. A closed kinetic chain is the distal end of the chain is fixed or in contact with the surface. For example, including performing squats or push-ups, where the hands or feet are in contact with the ground. That's closed kinetic chain. In a kinetic chain, forces generated at one joint or segment are transmitted through the chain to other joints or segments. Forces can be transferred sequentially or simultaneously depending on the movement pattern and task requirement. Kinetic chains influence muscle activation patterns. Movements in one joint or segment can trigger coordinated muscle activation or inhibition in other joints or segments within the chain. The coordinated muscle activity helps optimize movement efficiency and force production. Kinetic chains play a role in maintaining joint stability and mobility. The mobility of one joint affects the stability and mobility of adjacent joints within the chain. Dysfunctions or imbalances within the kinetic chain can lead to altered movement patterns and potential injury risk. When there is a dysfunction or limitation in one part of the kinetic chain, the body may compensate by altering movement patterns and redistributing forces. These compensations can lead to inefficient movement mechanics, increased stress on certain structures, and potential overuse injuries. Understanding the concept of kinetic chains allows for a comprehensive analysis of human movement and interplay between the various joints and segments. It helps in assessing movement efficiency and identifying movement dysfunctions and designing targeted interventions to improve performance or address movement-related issues. Here you can see these are examples of the muscle actions associated with each joint, and when you're looking at the different types of muscle actions, I recommend that you go through this and have an understanding of exactly what is associated with each joint. It can help you in learning anatomy, number one, and for those of you who want to go on for PT school can really be helpful. And this is another example. So some steps to identify muscle involvement and action for human movement. First, you want to identify the joint movement. Then identify the effect of an external force on the joint movement. Understanding which muscles are controlling a movement and how modifying the exercise affects these muscles is key in selecting appropriate exercise for a given goal. Identify the type of muscle action you want to see. Is it isometric, eccentric, whatever it is. Identify the plane of movement. So is it in the frontal plane, the sagittal plane, or transverse? Determine which side of joint axis are muscles lengthening or shortening. And use answers from steps 3 and 5 to determine which muscles are producing or controlling the movement. When it comes to exercise, most methods of resistance can be classified as either constant or variable. Constant, as the name implies, means that the weight load on the muscle stays the same throughout the exercise. Therefore, the amount of resistance used is determined by the sticking point or the weakest point of the exercise. A form of dynamic resistance exercise in which load does not vary during the exercise. Constant resistance exercises use simple equipment such as free weights, which can be moved by concentric and eccentric muscle actions. Free weights, machines with fixed resistance, body weight, cable pulleys, or other equipment are also considered. Variable resistance requires differing degrees of force to be applied to the target muscle to create constant resistance, compelling the muscle to work harder to meet the demands of the exercise. And a variable resistance arm curl, the forces applied to the bicep are variable at each stage of the curl in order to maintain the same resistance throughout the trajectory of movement. Plate-loaded machines, can-based resistance machines, elastic tubing bands, and chains are just some examples of means of that particular type of exercise, variable resistance. Now, accommodating resistance devices, typically we see the same approach of adding bands to squats to help with max strength, or using chains to help bring up a bench press that may be lagging. Occasionally, a coach will support the use of bands and chains as a replacement to Olympic lifts, almost as an either-or option for power development. Selection of the type of resistance, whether constant, variable, or accommodating, is an important factor in designing a safe and effective exercise program. And these are my references. That's all that I have for you today. I look forward to talking with you again. Have a great day.